Today's lecture is concerned with two of the transformation factors which allow us to convert from one form of payment to another. In particular, we'll be looking at the sinking fund factor and the series compound amount factor. You'll recall this diagram as one you've seen before, which shows the transformation factors between different kinds of payments. We have a present worth, money today, a future worth, money n periods from now, an annuity, which is a series of equal payments over n periods, and a gradient, which is a series of payments that increase in value over time. And the conversion factors allow us to find equivalent payments of these different types. Today we'll be looking in particular at the relationship between a future worth and an annuity. There are two transformation factors involved here. The sinking fund factor allows us to convert from a future worth to an annuity at a given interest rate and a given number of periods, capital N, while the series compound amount factor allows us to convert from an annuity to a future worth at a given interest rate and a given number of periods N. Before we start into the development of formulas for these transformation factors, I'd just like to remind you briefly of the definition of an annuity. An annuity is an equally spaced series of payments, which I can illustrate by these arrows on this cash flow diagram. The number of payments are n in total, where in this case n equals 6, and the symbol we use for an annuity is a capital A. This can be contrasted with a future worth, which is what we'll be converting to annuities to and from, which is just a single payment at some time in the future. In this case, it's 9 periods in the future. So n is equal to 9. The first of the two conversion factors is the sinking fund factor. It allows us, again, to go from a future worth to an annuity for a given interest rate in a given number of periods. And I'll be developing this formula in a minute, but in order to provide a means for developing the formula, I'd like to first present an example problem. In this example problem, the Waterloo Go-Kart Club has decided it wants to build a clubhouse and a track 5 years from now. It wants to accumulate the $50,000 needed by setting aside the same amount of money from its dues at the end of each year. So it's not building the track until 5 years from now, but it's saving up the money to do so. This process of putting money aside to save up for something in the future is called a sinking fund, and this gives rise to the name of this transformation factor, the sinking fund factor. We're given an interest rate of 10%, and we want to know how much should be saved each year. We can look at this problem just from our intuition, and if we have 5 years of savings and we want $50,000, well, our common sense would say we should save about $10,000 a year, because 10,000 times 5 is $50,000. But we know that each year we'll be putting the $10,000 that's saved, or the amount that's saved, into the bank and getting some interest on that money. So in fact, because we're earning interest on the money we're saving, the amount we need to put aside each year is really less than $10,000. And the problem really is, how much exactly less than $10,000? One common sense way of doing this, because we know how to find the future worth of money using our compound amount factor, we can, by trial and error, select some amount that we're going to save each year and see if we in fact accumulate the $50,000 over the 5 years. Let me show you the logic of what I suggested. Let's say we take a guess. We know the amount being saved is going to be less than $10,000. Let's take a guess that it's $9,000. So if at the end of year 1 we save $9,000, then because it's at the end of year 1, it'll be accumulating interest over 4 years. Because we're saving up for 5 years from now. At the end of the first year, it means that 1 year's passed, and there's 4 years left of savings. So the future worth 5 years from now of the $9,000 saved at the end of the first year, using our compound amount formula, will be $9,000 times 1 plus the interest rate, which is 1.1, raised to the fourth power, which is the number of years that will be earning interest. And that's equal to $13,176. So the idea is that $9,000 we saved at the end of this year will have accumulated to a total of $13,000 plus a little bit at the end of 5 years. If we put aside the same $9,000 at the end of the second year, well, it's going to accumulate interest for only 3 years, not the 4 years. And the amount it's going to accumulate at the end of the 5 years is going to be less. It's going to be $9,000 times 1.1 cubed. And that works out to be 11,979. I think you can understand the logic here. So if we are saving the $9,000 at the end of each year, the amount that's going to accumulate is going to be less the later in the 5-year time period we're dealing with. And we can figure out exactly what it is using our compound amount factor. And I'll just fill in these numbers here. And finally, at the end of the 5th year, well, we're saving our dues at the end of the 5th year, but they're not collecting any interest because they're just there, and we'll be spending them immediately on the clubhouse and track. Whereas in previous years, the amounts we've set aside have accumulated interest. So the total amount we would have saved, setting aside $9,000 each year, is simply summing these total future amounts, which works out to be $54,945. So the idea here is we took a guess at the amount we have to save each year. We calculated the future amount for each of those year savings and added them together to give a total future amount that would be saved over the 5 years. We can see it's more than necessary. This tells us that the $9,000 was too much. And we could go back and choose a different amount, say $8,500, and work it through in this manner until we finally narrowed in on the $50,000. That would be one way of solving this problem. There's a better way, of course. But what I want to do is use the idea we had here of calculating these future worths to develop a formula for doing so without having to go through this trial and error kind of process. And the way we do that is this. Rather than saying a guess of $9,000, we'll just use a symbol. We'll say, at the end of each year, we're going to save $8. So at the end of the first year, end of the second year, end of the third year, end of the capital N minus 1th year, and at the end of the nth year, we're saving $8. The future worth, well, it's going to be that $8 using the compound amount formula. It'll be times 1 plus the interest rate raised to the power of the number of years left until n. Well, just as in our trial and error example, this 4 was how many years left at the end of the first year, because we're looking to save for 5 years, is total number of years minus 1. That's what this exponent here is. It's capital N minus 1. For year 2, it'd be 1 plus I, capital N minus 2, and so forth. Down to here where we have A times 1 plus I to the first power, because there's only 1 year left, and the last year is just A times, if you like, 1 plus I to the 0, which is A. And we can total all those future worths up to give us one expression for the future worth of this series of payments, this sinking fund series of payments. So we can add that up, and we get our future worth. And what we get is a kind of an awkward expression. But what we're going to do is simplify it. We can pull out the A, and we get 1 plus I to the capital N minus 1 plus 1 plus I to the capital N minus 2. And we can go plus dot 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 1 plus I to the 1 plus 1. Rather long expression there. But what I'm going to do, I'm going to do this little sleight of hand here in this expression. I'm going to multiply both sides by, both sides being the f on the left and this long expression on the right, by 1 plus I. And I end up with f times 1 plus I. And that 1 plus I can move through all these elements of this long expression and simply raise the exponent by 1. So that's then 1 plus I to the n plus 1 plus I to the n minus 1 plus dot 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 1 plus I squared plus 1 plus I. Doesn't look like I gained much there, but what we can do now is subtract the first equation from the second. And if we do that, all the middle terms fall out. Because what I end up with is, on the left, f times 1 plus I minus f. And on the right, I get the a, but the 1 plus I to the n minus 1 subtracts out. So we get 1 plus I to the n, and all the subsequent terms, except the very last one over here, which becomes a minus 1. Now also we have this f times 1 plus I minus f becomes fi. And that's equal to a times 1 plus I to the n minus 1, so that a is equal to f times I over 1 plus I to the n minus 1. This gives us a very simple relationship between the annuity and the future worth, so that our conversion factor is this part, the I over 1 plus I to the n minus 1. Now that was kind of a complicated development. I won't be doing this depth of derivation in subsequent derivations of these formulas. But I wanted to go through this once with you, so you can see that these actually have a logical basis to them. They aren't just drawn out of a hat. And we can use this formula now, which is fairly straightforward, to convert any future worth to any annuity for any given interest rate or number of periods. Going back to our original problem then, we have our future worth of $50,000. We have interest rate of 10%. We have a number of periods of 5. We can then see that the annuity we need is 50,000 times 0.1 over 1.11 raised to the 5th power minus 1. And that works out to be $8,189.87. So the answer to the problem then is that the Go-Kart Club should put aside about $8,200 a year. Now the corresponding the reciprocal of the sinking fund factor is a uniform series compound amount factor, where we go from an annuity to a future worth. And it's simply the reciprocal. So we just simply take the sinking fund factor and exchange the denominator and numerator. So that's then 1 plus I to the n minus 1 over I. And a quick example of the uniform series compound amount factor. This year's electrical engineering class has decided to save up for a class party. Each of the 90 people in the class is to contribute 25 cents per day, which will be placed in a daily interest savings account that pays a nominal 8% interest. The class party is in 14 weeks. How much will be saved? Assuming everybody makes their payments on time. So here we have an annuity. The annuity is 25 cents. The interest rate, it's a nominal 8% interest, and it's a daily interest savings account. So we simply take the 8% and divide by 365. Because it's nominal, we can do that. And the number of periods, it's 14 weeks, but we're talking about daily interest rate, so it's really 14 times 7, which is 98. Substituting that into our formula, we find the future worth is going to be equal to the annuity, 25 cents, times 1 plus 0.08 over 365 minus 1. That's raised to the 98th power over 0.08 divided by 365. And that works out to be $2,246.92. So the formulas here are quite straightforward. I went through a derivation, which is useful, I think, to demonstrate that these formulas come from somewhere. Applying to the problems is simply a matter of recognizing that you have an annuity and you want a future worth, or conversely, you have a future worth and you want an annuity, and determining what the appropriate interest rate and the number of periods are. Thank you.